Alright, today let's have a look at topic 10, geometric inequalities. So in this topic, we will explore three geometric inequalities involving triangles. First, we will examine how the order of the length of the side is related to the order of the measures of the angles in the triangle. Then we'll learn how to tell if a triangle is acute or obtuse just by considering its side length. Finally, we'll explore the most widely used geometric inequality of all, which is the triangle inequality. Like many of the most useful mathematical tools, the triangle inequality is so simple it's almost obvious, but it can be used to develop many non-obvious solutions to complex problems. Okay, first, let's consider the relationship between size and angle. So first, let's have a look at the relationship in a right triangle. Well, probably by instinct, we can discover that the longest side in the right triangle might be the hypotenuse, right? But we all have to work through a few cases to prove it though. So first of all, can you prove that the hypotenuse of a right triangle is longer than each of the other two sides of a triangle? Okay, let's start by considering this simple question here. Okay, I'll give you 2 minutes to consider these questions, and we'll have a look at the solution together, okay? All right, any ideas? So to prove this, we can make use of the Pythagorean theorem, right? So for example, we could let AC be the hypotenuse of triangle ABC. Such as illustrated here in this diagram, AC is hypotenuse. Then the Pythagorean theorem tells us that we have AC squared equals AB squared plus BC squared, right? And because AB squared is positive and BC squared is also positive, we must have AC is greater than AB, right? And also AC is greater than BC. You get it? Hence, the hypotenuse of a right triangle is longer than each of the other two sides of the triangle. we have proved this statement, right? So taking care of the longest side in the right triangle was pretty easy, right? And now let's take a look at the obtuse triangles. So let's consider another question here. Can you prove that in an obtuse triangle, the side opposite the obtuse angle is the longest side of the triangle? Okay, for example, if we have a obtuse triangle here, A, B, C, like this, how do you prove this? We want to prove AB is greater than AC and AB is greater than BC, right? Okay, any ideas? So we have already know that the hypotenuse of a right triangle is the longest side of the triangle, right? So we could make use of some right triangle. If there is no right triangle there, we could make one, right? So we want to show that AB is the longest side of our triangle, so we could make it the hypotenuse of a right triangle by drawing the altitude AD from A, right? So if we draw the altitude from A here, call this point as D. And because AB is the hypotenuse of triangle ABD, right? So in right triangle ABD, we have AB must be greater than BD, right? We have already proved this because in the right triangle, the hypotenuse is the longest one. So AB is longer than BD, right? And from diagram, we also have BD is longer than BC, right? Therefore, we have AB is longer than BD, BD is longer than BC. Therefore, we have AB is longer than BC, right? So at least we have already proved AB is longer than BC. Similarly, we can draw an altitude from B to show that AB is longer than AC. So similarly, next we could draw altitude BE from B as shown in the diagram. Then we could use the right triangle. So in right triangle ABE, AB is a hypotenuse, right? So AB is longer than AE, right? And we also have AE is longer than AC. Therefore, AB is longer than AE, AE is longer than AC. Therefore, we have AB is longer than AC, right? So we have proved AB is longer than BC and AB is longer than AC, right? Therefore, we know AB is the longest side in triangle ABC, right? Did you get it? So it's not that difficult in an obtuse triangle as well. In a summary, in an obtuse triangle, the side opposite the obtuse triangle is also the longest side of a triangle. We can easily prove this, right? And now let's consider the next type of triangle. We have acute triangles, right? So could you prove this? Let triangle ABC be acute, which means all of the interior angles are acute, with angle B is larger than angle C. Can you prove that AC is longer than AB? Okay, I'll draw you a diagram to illustrate the situation here. Suppose we have a obtuse triangle, acute triangle ABC like this. Any ideas? Usually you'll need to use what we have learned so far, right? We have proved that the hypotenuse of a right triangle is the longest one. We have proved that the side opposite the obtuse angle is also the longest one. So although it's not clear how we can build a right triangle to directly compare AB and AC, we could build a obtuse one, right? First of all, for example, we could draw altitude AX here and locate a point D on BC, the line BC, such that AD equals AC. So the question is D here or here? Such that AD equals AC. Well, intuitively, D should be beyond B on the ray CB, right? Like this. But still, you need to prove that, right? Okay, so first of all, let's see if we can prove that. Okay, so we could right here draw altitude AX as shown in the diagram and locate a point D on the line BC. So here we need to use a line because you don't know whether it's on the left side of B or the right side of B, right? We don't know where the point D is. Locate point D on line BC such that AD equals AC. And because we have AD equals AC, we have angle ADX should equal angle C, right? Therefore, we have angle D must be less than angle ABC. You see that? Because as angle B is larger than angle C. So here, angle D equals angle C. ADX equals angle C. ADX is actually angle D here. So angle D is less than angle ABC, right? And because angle D also equals 90 degrees, subtracted by angle DAX. And angle ABC equals 90 degrees minus angle BAX. Therefore, we have 90 degrees minus angle DAX. That's angle D, right? Less than angle ABC, which is 90 degrees minus angle BAX. Therefore, we have proved angle BAX is smaller than angle DAX, right? If angle BAX is smaller than angle DAX here, then we know D must be on the left side of B, right? Therefore, we can conclude D is beyond B on the ray, say B, as shown in the diagram. And because angle ABC is acute, because it's in a acute triangle, right? Then we know angle ABD is 180 degrees minus angle ABC. Angle ABD must be obtuse. And therefore, if we have an obtuse angle here, then we have already proved that the side opposite obtuse angle is the longest side of the triangle, right? So we can make use of the conclusion here. Because angle ABD is obtuse, so in the triangle ABD, because angle ABD is obtuse, so we have AD is the longest side, therefore we can prove AD is larger than AB, right? You see that? And because we also know that AD equals, oh sorry, yes, AD equals AC, right? AD is larger than AB, and we can prove that AC is larger than AB, right? So have a look at the proof here, and let me know if you have any questions, okay? So this makes us prove AC is larger than AB. So in acute angle, in acute triangle, if you have a larger angle, the corresponding side is also larger, right? The side opposite to the larger angle is also longer. Now, if you have finished this, consider if the reverse statement is also true, which means if triangle ABC is a acute triangle, if we have AC larger than AB, can you prove that angle B is larger than angle C if the reverse statement is also true? It seems true, but still you need to prove that, right? All right, so let's consider the reverse statement here. If triangle ABC is a acute triangle, can you prove that if AC is larger than AB, then we have angle B is larger than angle C? Well, actually, the reverse statement is much easier than this one, right? I'll give you 2 minutes to think about this, and we'll have a look at the solution together, okay? Alright, let's have a look at the solution together. So suppose we have a acute triangle ABC. Then we only have three possible cases, right? One of them must be true. So case 1, we could have angle B is larger than angle C, right? In this case, we have already proved that if you have angle B is larger than angle C, then we must have AC is larger than AB, right? Of course, there is a second case possible, which is angle B equals angle C. This is also possible in an acute triangle, right? And in this case, we have already learned that if angle B equals angle C, then AC must equal AB, right? And the third case is angle C could also be larger than angle C. And we have already proved according to this example. Then in this case, AC, mistake here. Angle B, in this case, angle B could also be smaller than angle C, right? In that case, AC must be smaller than AB, right? Only one of the cases here is true. So we are given that AC is larger than AB. The only one of these cases that can lead to AC is larger than AB is case 1 here, right? Did you get it? So we could say we are given that AC is larger than AB. The only cases here, only one of these cases that leads to AC is larger than AB is case 1. So we can deduct that angle B must be greater than angle C, right? Make sure you understand this logic, okay? So a statement is true does not necessarily mean the reverse statement is also true. You need to use logic reasoning to prove it, okay? And this logic here is correct. Did you get it? And then in a summary, we can summarize the above statement like this. In any triangle, the longest side is opposite the longest angle, and the shortest side is opposite the smallest angle. The middle side, of course, is therefore opposite the middle angle, right? In other words, in a triangle ABC, AB is longer than or equal to AC, which is longer than or equal to BC, if and only if angle C is larger than or equal to angle B, which is larger than or equal to angle A. Did you get it? So this can summarize all of our discoveries so far. No matter if the triangle is a acute triangle, right triangle, or obtuse triangle. Okay, have a look at the summary here, and we'll use these facts on a couple of problems later. Okay. Alright, if you have finished, let's consider another example here. So given the angles as shown on the right, order the lengths A, B, BD, CD, BC, and AC from greatest to least. Also note that if you are given a diagram is not necessarily to scale, okay? So you can't use your ruler to measure them. Just try to prove your statement. Okay, if you finish, please give me your answer in chat box, okay? Alright, let's have a look at the solution together then. So first of all, we can consider triangle ABC. In that triangle, we have angle A is larger than angle B, which is larger than angle C, right? Therefore, we have BC is larger than AC, which is larger than AB, right? And in the other triangle BCD, we have angle B is the largest one. Angle B is larger than angle C, which is larger than angle D. In that case, we have CD is larger than BD, which is larger than BC, right? And luckily, we can link them together. Therefore, we have CD is the largest one, followed by BD and BC, and we link them from here. BC is larger than AC, right? And AB is the shortest one. Did you get it? Any questions? Okay, if not, let's consider another practice. In triangle ABC, the median AM is longer than half of BC. Can you prove that angle BAC is acute? Well, let's draw a diagram for you to illustrate this situation here. Basically, we have a triangle ABC, and we have a median here. So M is the midpoint of BC. Okay, so let's have a look at the solution together. So we'd like to prove something about the angle, right? But all we are given here is a inequality regarding length. So we could use the length inequality to get some angle inequalities to work with. So first of all, in triangle ABM, we have AM is larger than BM, right? Because that's AM is longer than half of BC. So BM is half of BC. So we have AM is greater than BM. And therefore we have the angle opposite to this side is B. So angle B must be greater than the angle opposite to the side BM, which is angle BAM, right? Then we consider the other triangle here. In triangle ACM, we have AM is longer than MC, right? Therefore, we know angle C must be larger than angle CAM, right? We want to prove something about BAC, therefore we could add these two inequalities together. And this gives us the left side is angle B plus angle C, and that's larger than the right side, which is angle BAM plus angle CAM, which equals angle BAC, right? And because we know angle B plus angle C plus angle BAC equals 180 degrees, then we know that 180 degrees minus angle BAC, that's angle B plus angle C, right, is larger than the right side, angle BAC. And therefore we know angle twice of angle BAC is less than 180 degrees, therefore angle BAC is less than 90 degrees, right? Therefore angle BAC is acute. Did you get it? So we can use the relationship between length inequality and angle inequality to prove this. Any questions? Okay, then if you don't have any questions, next let's have a look at a Pythagorean-like theorem but applied to non-right triangles. So previously we have learned that if you have a right triangle ABC, then AC square, sorry, C should be here, so AC square plus BC square must equal AB square. So this is Pythagorean theorem tells us that, right? But what if AC square plus BC square does not equal AB square? For example, if we let angle C in triangle ABC be acute, can you prove that AC square plus BC square is greater than AB square? Okay, let's draw a diagram to illustrate the situation here. Any ideas? if you see squared side lengths, then that makes us count for right triangles, right? So in that case, we could draw the altitude AX as shown here. Then this will give us a couple of right triangles, right? So first of all, we could draw altitude AX as shown here. Then from right triangle ABX, we have AB square plus, AB square, AB is hypotenuse, AB square equals AX square plus BX square, right? And clearly BX is less than BC. And we also know in right triangle ACX, we have AX is less than hypotenuse AC, right? Therefore, we have the following relationship: AB square equals AX square plus BX square. Then we can substitute AX using AC because AX is less than AC. So if we substitute AX using AC, then that must be less than AC squared, right? And because BX is less than BC, so if we substitute BX using BC, this still makes this inequality true. So that means that is less than AC squared plus BC squared, right? So this proves that AB is smaller than AC squared plus BC squared, right? Okay, so you might be wondering that why did we use the fact that angle C is acute? So if you look closely, you probably wonder why must X be on the segment BC, right? If angle B and C are both acute, then altitude AX must meet BC. Our proof here therefore doesn't address the case where angle B is obtuse, right? However, in that case, we have AC is larger than AB. So obviously, AC squared plus BC squared must be larger than AB squared, right? What I mean here is if angle B is obtuse, like this, then obviously we have AC is larger than AB, right? So we have AC squared plus BC squared must also be larger than AB squared in the second case, right? Okay, now let's consider another statement. If we let C in triangle ABC be obtuse, can you prove that AB squared is larger than AC squared plus BC squared? Again, let me draw you a diagram to illustrate the situation here. Again, we could start by drawing an altitude, right? Because this seems like a Pythagorean theorem, so we could make use of some right triangles there. So for example, if I draw a auxiliary line like this, draw altitude AD as shown. Okay, let me give you some hint. So could you prove this inequality is actually true? Alright, so how about we consider right triangle ABD first. So in right triangle ABD, we have AB squared equals AD squared plus BD squared, right? So in order to get BC term and the AC term in our equation, we also have another right triangle to use. In right triangle ACD, we have AD squared equals AC squared minus CD squared, right? And also we have BD equals BC plus CD. Therefore, we could make use of these equations. AB squared equals AD squared plus BD squared, right? And substitute AD squared using AC squared minus CD squared. And substitute BD using BC plus CD. Therefore, we have plus BC plus CD squared. And expand this right side. This gives us AC squared minus CD squared plus BC squared plus twice of BC times CD, right? Plus CD squared. Then that cancels a CD squared there. And gives us AC squared plus BC squared plus 2BC times CD, right? So we know that last term must be positive because BC and CD are sides, right? This term it must be positive. Therefore, we know AB squared must be greater than AC squared plus BC squared because there's another additional term 2BC times CD, right? Did you get it? have a look at the two questions we have proved. So if if triangle ABC is a acute triangle, oh sorry, if angle C in triangle ABC is acute, then the opposite side AB square is less than AC squared plus BC squared, right? And if angle C is the obtuse triangle, if angle C is the obtuse angle in the triangle ABC, then the opposite side AB squared is larger than AC squared plus BC squared. So the problem is that, well, if you recall that the reverse statement of the Pythagoras theorem is also true. We have already proved that, right? Basically means if the size of triangle satisfies a squared plus b squared equals c squared, then the angle is right triangle, and reverse statement is also true. If we have a right triangle, then we have a squared plus b squared equals c squared. So now let's investigate if the converses of the inequalities we have just discovered are also true, which means can you prove that if AB squared is larger than AC squared plus BC squared, then angle C is obtuse. And can you also prove that if AB squared is less than AC squared plus BC squared, then angle C is acute. Well, if we substitute the inequality signs to equality signs, then we know that angle C must be a right angle, right? Now, if we use the inequality signs, can you prove these statements are also true? Okay, let's do this together. So again, we can consider three different cases, right? In a triangle ABC, there are only three cases: whether angle C is acute, right, or obtuse, right? So case one is angle C is acute. So in that case, we have just proved that if angle C is acute, then we will have this inequality here, right? Then that gives us AB squared must be less than AC squared plus BC squared. And there is another possibility, case number 2, which means angle C it could be right, right? If angle C is right, then we have the Pythagoras theorem. This tells us that AB squared equals AC squared plus BC squared. We have already proved this, right? And last case, case number 3, is angle C could also be obtuse. In that case, we have already proved, according to this question here, if angle C is obtuse, then we have AB squared is larger than AC squared plus BC squared, right? So each possible triangle ABC must fall under exactly one of these cases. Only in the first case. Only in the first case here. We have AB squared is less than AC squared plus BC squared. So if AB squared is less than AC squared plus BC squared, we can conclude that angle C is acute, right? Can you see the logic here? each possible triangle ABC must fall under exactly one of these cases. Only one case is possible. So which case will give us AB squared less than AC squared plus BC squared? Only the first case, right? And the first case tells us that angle C is acute. Therefore, we can prove that if AB squared is less than AC squared plus BC squared, then angle C must be acute. Did you get it? Therefore, we could rewrite this using if and only if. Bidirectional arrows. And we have already proved the second one is also true, right? We could also use bidirectional arrows. And last, similarly, only in the third case, we have AB squared is larger than AC squared plus BC squared. So we can conclude that in that case, angle C is obtuse. So again, this is if and only if. You get it? Okay, so now let's make a summary here. We can now relate the squares of the sides of a triangle to the angles of a triangle now. So angle C of triangle ABC is acute if and only if AB squared is less than AC squared plus BC squared. Angle C of triangle ABC is right if and only if we have AB squared equals AC squared plus BC squared, right? And next, angle C of triangle ABC is obtuse if and only if AB squared is larger than AC squared plus BC squared. Did you get it? Okay, now let's take a 10 minutes break, and after that we'll try some of this information on some problems. Okay? See you in 10 minutes. All right, let's do a practice here to use what we have learned so far to solve this problem. So in triangle XYZ, we have xy equals 11 and yz equals 14. For how many integer values of x is triangle XYZ acute? All right, let's have a look at the solution together. So in order for triangle XYZ to be acute, all three of its angles must be acute, right? So using the given side lengths and or inequalities here, we see that we must have 11 square plus 14 square larger than xz square, right? And we also have 14 square plus xz square must be greater than 11 square, and 11 square plus xz square must be larger than 14 squared, right? All of these inequalities must be satisfied. So this is equivalent to say xz square must be less than 317 and xz square must be greater than negative 75 and xz square must be greater than positive 75. So the second one is obvious, right? The second one is always fulfilled. So that leaves us xz square must be less than 317 and must be greater than 75, right? So combining these two gives us that xz square must be greater than 75 and less than 317, which is equivalent to say, well, also note that xz is an integer. The length of xz is an integer, right? So this gives us xz must be between 9 and 17. Close interval, right? Therefore, there are 9 integer values of xz such that triangle XYZ is acute. Any questions? Okay, if no questions, next let's have a look at another important inequality, which is the triangle inequality. The triangle inequality answers the question, when can 3 given segment lengths be the side lengths of a triangle? The answer to this question is both more obvious and more powerful than the other inequalities we have already learned in this lesson. So we'll start with a proof of this simple inequality and then show why the inequality is so powerful by using it to solve a variety of problems. Alright, so let's consider this example here. Can you prove that in any triangle the sum of the two sides is greater than the third side? Well, this is called the triangle inequality. And then, if you have finished that, the triangle equality is often written as sum of the two sides greater than or equal to third side. So why? Where does the or equal to come from? And the third one is actually the reverse statement, right? So if A, B, C are positive numbers such that A plus B is greater than C, A plus C is greater than B, and B plus C is greater than A, then can you prove that there exists a triangle with set lengths A, B, and C? Okay, I'll give you 2 minutes to think about this question, and we'll have a look at the solution together, okay?
I thought we have learned like the first theorem, like the sum of two sides is greater than the third side. In the first lesson, we've learned about triangles. I mean, like, this is supposed to be a really basic theorem in a triangles. Like, it's supposed to be the first thing we learn about triangles. Yeah.
Alright, let's try to do this together. First one proves that in any triangle, sum of the two sides is greater than the third side. So we've had so much success building right triangles, right? So again, we could make use of some right triangles here. So, well, let's separate cases here. So suppose we have a acute triangle, case one. Well, suppose triangle ABC is acute. We could draw altitude BD. Then forming two right triangles, we then have AB is greater than AD, right? This is what we have learned so far, right? In the right triangle, AB is greater than AD, and BC is greater than CD. Adding these gives us the desired AB plus BC is greater than AD plus CD, which equals AC, right? We can do the same for each angle, showing that each side is less than the sum of the other two sides. Can you see that? Not that difficult, right? So, but we have another case. Well, angle ABC could also be right or obtuse triangle. Well, in the second case, triangle ABC is right or obtuse. So that means angle B is greater than or equal to 90 degrees. Then clearly in that case we have AC is larger than AB and AC is larger than BC. Right? So in that case we definitely have AB is smaller than AC plus BC. And BC is smaller than AC plus AB, which is much simpler than the first case, right? So all we have left here is to prove AC is less than AB plus BC, right? Once again, we can make use of some right triangles there. So for example, we could draw altitude BE here. Then this gives us AB is larger than AE and BC is larger than EC. Therefore, we have AB plus BC is larger than AE plus EC, which equals AC, right? Therefore, in both cases, we can prove that sum of the two sides is always greater than the third side. You get it? Okay, now answer the second question. So where does the or equal to come from? We have seen above that if A, B, and C are not collinear, A, B, and C are not collinear, then there cannot be equality, right? However, when A, B, and C are collinear, like this, such that B is between A and C, we are collinear, then we have AB plus BC equals AC. If A, B, and C are collinear, we call the resulting triangle ABC. In that case, well, if you consider this as a triangle, then in that case, triangle ABC is a degenerate triangle. We call this is a degenerate triangle. But usually, the term triangle only refers to non-degenerate triangle. Sorry, non-degenerate triangle. Non-degenerate triangle. Okay, so typically the term triangle only refers to the non-degenerate triangle, which is shown on the left side. And note, note that when B is on the segment AC, we still have AC plus BC is larger than AB, and AC plus AB is greater than BC. In addition to AB plus BC equals AC, right? So the triangle inequality is still satisfied with small modification. So in a summary, we have the following triangle inequality. The triangle inequality states that for any 3 points, A, B, and C, we always have AB plus BC is greater than or equal to AC, where equality holds if and only if B is on the segment AC. Therefore, for non-degenerate triangles, we have AB plus BC is always greater than AC. You get it? Alright, so this is a triangle inequality, and we have another question to answer, right? Is the reverse statement is also true, which means if A, B, and C are positive numbers, such as A plus B is greater than C, A plus C is greater than B, and B plus C is greater than A, then can you prove that there must be a triangle with side lengths A, B, and C? You see the difference between the third question and the first question? Well, let's have a look at the proof here. So we could assume, so without loss of the generosity, we just assume A is larger than or equal to B, which is larger than or equal to C, and let our triangle be triangle ABC with AB equals C, AC equals B, and BC equals A. Then we can start building our triangle. So the key is to prove if we can build such a triangle, right? If you can build one, then we can prove that must be a triangle like this, right? So let's say, suppose this is B and C, and BC is A. This length is A. So we can start building our triangle by drawing BC with length A. This is possible by using a straight edge and a compass. We know that A must be on a circle with center B here, and radius AB equals C. So we could draw a circle here. So let's call this point E. Okay, so BE is actually C. And we could draw another circle on the right side, just here. Okay, it's out of the page, so I'll just draw part of it. And we call this point D. So CD equals B. So because A is larger than or equal to B and larger than or equal to C, we know that BC is larger than or equal to AC, which is larger than or equal to AB. Therefore, the radius of circle, the radius of circle B is no greater than BC, right? So circle B must intersect section BC at some point. So let's call this point E here. Similarly, angle C must meet segment BC at some point D. So let's call this point D here. Since B plus C is larger than A, we know that BE plus DC equals B plus C, which is greater than A, which equals BC, right? Since BE plus DC must be greater than BC, we know that D cannot be on EC. In other words, our two circles must meet, right? They could not be like this. In that case, it could not meet, right? And we also know that they must meet at 2 points here, which means they cannot meet like this, right? Therefore, that gives us a triangle ABC like this. This is our point A. You get it? Okay, so again, this concludes the triangle inequality. Also note that it is true for both directions, all right? Okay, now let's use this inequality to solve some questions. So let's consider this question here. In how many ways can we choose 3 different numbers from the set 1 to 6, such that 3 could be the size of non-degenerate triangles? So note that the order of the chosen number doesn't matter. So we consider, for example, 3, 4, 5 to be the same as 4, 3, 5. How many possibilities do we have here? Here, I'll give you a hint here. So we first notice that if we have 3 numbers to consider as possible side lengths of a triangle, we only need to make sure that the sum of the smallest 2 is greater than the third. That'll make these 3 points a triangle, and then a non-degenerate triangle, right? Also make sure you see why. Alright? Because sum of the largest two sides is always greater than the third one, right? You don't have to prove that. So as long as you make sure sum of the smallest two is greater than third, then you can have a triangle. Also, the largest one plus the medium one is also large. The sum of the largest one and the middle one is also larger than the smallest one. This is also true, right? This is necessarily true. So you only need to ensure the sum of the smallest two is greater than the third one. In that case, let's do some case work here. So case 1, the smallest side has length 1. In that case, no triangles can be made with the 3 different lengths from our set, right? If we include 1 as a length, because 1 plus 3 cannot be larger than 3, 4, 5, 6. 1 plus 3 cannot be larger than 4, 5, 6, right? So this is not possible. In that case, no triangles can be formed. You get it? So the second case is that smallest side has length 2. So in that case, we could have the other two sides must be 1 apart. So we could have 2, 3, 4 is a possible set, and 2, 4, 5 is another possible set, and 2, 5, 6 is another possible set, right? And case number 3, smallest side has length 3. There are only 3 possibilities, and they all work, which is set 3, 4, 5, and the set contains 3, 6, 3, 4, 6, right? And case number 4, smallest side has length 4. In that case, the only possibility is the set contains 4, 5, 6, right? Which also works. So adding this up, we have 1, 2, 3, 4, 5, 1, 2, 3. I lost one here, right?
3, 5, 6?
Yeah, I lost one here. Sorry about that. 3, 5, 6 is also possible, right? So there are, so we have 7 possibilities. One, two, three, 4, 5, 6, and 7 triangles here, right? Okay, consider another question here. Can the length of altitudes of a triangle be in the ratio 2 to 5 to 6? Why or why not? All right, let's have a look at the solution together. So we don't know anything about the lengths of the altitudes of triangle are related to each other, right? We do, however, know a whole lot about the lengths of the sides of a triangle are related to each other. Therefore, we can turn the problem from one involving altitudes to one involving side lengths. So suppose the side lengths are A, B, and C. So the corresponding altitude are, let's say, HA, HB, and HC. Then we could use the area of the triangle to connect them together, right? The area of the triangle is, well, let's use the letter K to denote the area. So K equals 1/2 of A times HA. K equals 1/2 of B times HB. K also equals 1/2 of B, C times HC, right? Then the three lengths, the three sides, of the triangle is 2K over HA, 2K over HB, and 2K over HC, right? So suppose this is possible. Suppose the length of the altitudes of triangle be in the ratio of 2 to 5 to 6. Then if we let HA equals, let's say, 2x, then HB must equal 5x, then HC must equal 6x, right? The three sides are 2k over 2x, 2k over 5x, then 2k over 6x. Now, let's check if the sum of the smallest two sides is greater than the other one. Because these, the smallest two sides are this one and this one, right? So if we sum them up, we get 12k over 30k. Sorry about that. 10k over 30k, and this actually gives us 22k over 30k, right? And rewrite this using the common denominator 30k. Well, that equals 30k over 30x, right? Or I made sorry, there's a typo here. That should be x, not k. So apparently the sum of the two smallest sides is smaller than the other side. So this cannot form a triangle, right? So our assumption is not correct. Therefore, it's impossible to have a triangle with heights in the ratio 2 to 5 to 6. Did you get it? So let's say the conclusion is impossible. Okay, if no questions, let's consider another example. If you let AM be the median of a triangle ABC, can you prove AM is greater than AB plus AC minus BC over 2? Okay, let's draw a triangle ABC. AM is the median. Okay, I'll give you some hint. We can apply the triangle inequality to both triangle ABM and ACM, right? This means AM plus BM must be greater than AB, and AM plus CM must be greater than AC, right? So note that BM plus MC equals BC. We think to add these inequalities, which gives us 2AM plus BC is greater than AB plus AC. So do you have the desired conclusion now? Therefore, we have AM is greater than AB plus B plus AC minus BC over 2, right? Okay, so there is one last property we haven't talked about so far. So first of all, please write this down in your notebook because we're running out of time. So we're not gonna prove this in our class. I'll give you a question for you to do in your homework. Okay, so this is another important property. If circle O and circle P are tangent at point T. Tangent means they only meet at one single point. And then OPT are collinear. We'll often use this fact in problems with tangent circles by connecting the centers of the circles, knowing this line also goes through the point of tangency. This is true for circles that either externally or internally tangent. Okay, this is another important conclusion. Of course, we haven't proved this yet, right? So also try to prove this after this class. Consider this as your homework, okay? Circle O and circle P are tangent at point P, at point T. Such that neither circle passes through the interior of the other. Such circles are said to be externally tangent. Can you prove that O, T, P are actually collinear? Okay, try to prove this after the class, okay? And the main takeaway here is if O and P are tangent at point P, actually we can prove this. Then OPT are collinear. This is true for circles that either externally or internally tangent, which is shown here on the right. Okay, let's have a look at topic 11, which are some fundamental concepts related to circles. Alright, first of all, let's have a look at some basic concepts related to a circle. So if you have a circle here, then any segment that connects 2 points on the circle is called a chord. And if a chord passes through the center of that circle, then that chord is called a diameter of that circle. And half of the diameter is called radius. And if you have a line and there are two points of intersections of the line with the circle, then that line is called the secant line. Otherwise, if you only have one point of intersection between that line and the circle, then that line is called the tangent line of that circle. And the portion of a circle connecting 2 points on the circle's circumference is called an arc. And the area enclosed by an arc and the corresponding 2 radii is called a sector. And any area that is enclosed by a chord and corresponding arc is called a segment. Okay, clear? And of course, sometimes we also use the angle here. This angle here is called a central angle. Or if you see this arc here, then this angle here is also a central angle. A central angle of a circle is an angle with the center of the circle as its vertex. Of course, sometimes we use a central angle to help us to measure the length of an arc. The length of an arc, well, suppose this measurement is theta, then we could use theta over 360 degrees times the circumference of the whole circle, right? That's the length of arc. Of course, here theta must be in degree measurement if you use 360 as the denominator. Did you get it? So basically, we find the measure of an arc of a circle by considering what fractions of a circle of the arc is. For example, a whole circle is 360 degrees. So an arc that is 1/6 of the circle has to measure 60 degrees, right? So next we'll start with the length of the entire circle, which would be the perimeter of a circle. So basically, the perimeter of a circle is called the circle's circumference. And actually, the ratio between the circumference of a circle to its diameter is a constant. We call this constant as pi. So pi is a mathematical constant that is a ratio of a circle's circumference to its diameter, which is approximately equal to 3.14159. And pi is an irrational number. Which means that it cannot be expressed as a ratio of integers. Because pi is irrational, its decimal expression does not terminate and does not become periodic. In other words, it does not get to a point where the same set of numbers is repeated over and over. So there are no shortcuts to memorize digits of pi. So usually we use an approximation. Depends on which accuracy you need. For example, we usually take 3.14 as a approximation of the constant pi. So next, let's have a look at a practice. Okay, so basically this tells us that if you know the diameter, then you could find the circumference of a circle, right? And vice versa. And now let's take a example question here. If the circumference of a circle is 32 pi, can you find the circle's radius? So we know the ratio between the circumference to the diameter is pi, right? So in that case, if we let C be the circumference, and D be the diameter, we know that C over D gives us the constant number pi, right? That's the ratio between circumference to diameter. And of course, here we know the circumference, so D equals C over pi. In that case, C is 32 pi over pi, and this gives us 32, right? So the diameter is 32. Also, we know that the radius is half of the diameter. So if we let R be the radius, then we know 2R equals D. This gives us R equals half D, which is 16, right? So 16 is the radius of that circle. Did you get it? Okay, so in a summary, in a circle, if you let C be the circumference, D be the diameter, and R be the radius, we have this relationship here. C equals pi times D, which equals 2 pi R. Any questions? All right, then let's consider another question. If the length of a 72-degree arc of a circle is 15, what is the circumference of that circle? So in a circle, we have a arc that is 70 degrees here, and we know this length is 15. What is the circumference of that circle? Okay, so in order to facilitate our discussion, we could let the length of the arc be A, and let the let A be the length of the arc, let C be the circumference, of the circle. Then we have the following relationship. We know that the ratio between 72 degrees over 360 degrees is the ratio of the length of the arc over the circumference of the circle, right? These two ratios must be the same, right? And therefore we have 1 over 5 equals 15 over C, which gives us C equals 75, right? Did you get it? This is how you get the length of an arc if you know the central angle and the circumference of a circle, and vice versa, right? Any questions? Alright, then if you don't have any questions, let's consider another practice. Chord YZ of a circle with center O has length 12. The circumference of the circle is 24 pi. Could you find the length of the arc YZ? Okay, we have a circle here. I'll suppose this is a point Z. There's another point Y. This is a chord YZ and corresponding arc YZ here. Could you find the length of arc YZ? And if you finish, please give me an answer in the chat box, okay? Oh, by the way, if you don't have a input for pi in the chat box, you could also use these two letters, PI. Okay, so let's have a look at the solution here. So to find the length of the arc, usually we must find the central angle here, right? We don't have any information about angles here, however, so we start by figuring out some length. Since the circumference C equals 24 pi, right? And diameter is C over pi, which is 24. So we know the diameter is 24, and radius is half of the diameter, which is 12, right? So here r equals 12. The other side of the triangle is also 12, and we are also given that the third length here, the chord YZ, is also 12. So we know this angle here, YOZ, is 60 degrees, right? This is how we find the angle there. Therefore, we know the length of the arc YZ equals 60 degrees over 360 degrees times the circumference, which is 1/6 of 24 pi, which is 4 pi, right? And usually, if your result contains pi and the question does not ask you to use any approximation, you could just leave it there. Just use pi to denote the ratio between circumference and the diameter. You don't have to use any approximation if not required. Okay? Always keep your result in the exact form, which is 4 pi. Okay, any questions? All right, if no questions, let's have a look at another question. Chords A, B, and CD of circle O has the same length. Can you prove that AB equals CD? So arc AB equals arc CD. So let's draw a circle. Okay, this is circle O. We have some point A, B, C, D. Okay, so give you that the chord AB equal the chord CD. Can you prove the corresponding length of the arc AB also equals CD? Okay, let's have a look at the solution together. So we form two triangles by connecting A, B, C, and D to O, right? And then we have triangle ABO and triangle CDO. Because we have AB equals CD according to the given information, AO equals CO, and also BO equals DO. Then we have triangle ABO must be congruent to triangle COD according to SSS congruence, right? Therefore, we have the two central angles are equal. So angle AOB equals angle COD, right? So if the two center angles are equal, then the corresponding arcs must be congruent. Which means length of AB equals length of CD, right? Did you get it? Okay, so if you don't have any question here, consider if the reverse statement is also true. It seems like it's true, but you still need to prove that, right? So let's consider the reverse statement, which is if you have two equal arcs in a circle, can you prove that corresponding chords are equal? In that case, we have a circle here. If we know the two arcs, Wx equals Yz, so this length equals this length here. Can you prove the corresponding chords are equal? Which means, can you prove Wx equals Yz? Okay, have you finished? Not that difficult, right? You could say because arc Wx equals arc Yz, then the two central angles are equal, which means angle WQX equals angle YQZ, right? And because we have WQ equals QX equals QZ equals QY, all of these sides are radi of the circle, so they have equal lengths. Therefore, we have triangle WQX, must be congruent to triangle YQZ by SAS congruence. So we have the corresponding sides of the two triangles are congruent, which means WX equals YZ, right? Did you get it? So in a summary, this tells us a very important property in a circle. Probably want to write this down in a notebook. If two chords of a circle are congruent, then the arcs that they subtend or cut off are also congruent. Conversely, if two arcs of a circle are congruent, then the chords that they subtend them are also congruent. Okay, have you finished? All right, let's use what we have learned so far to solve a practice question here. So I'll give you 3 minutes to consider this question by yourself, and then we'll have a look at the solution together, okay? Alright, then let's consider the second case, where this angle here is 120 degrees, right? In that case, we connect A, B, and C to the center of the circle, of which the path is apart. Since we know more about the radius that we do about arcs, since arc AB is 120 degrees here, we know that C is the midpoint, so this point here is 60 degrees. This angle here is 60 degrees. This angle here is also 60 degrees, right? Therefore, OA equals OC equals OB. Therefore, we have triangle AOC and triangle BOC are both equilateral triangles, right? So we need to find the radius of the circle to finish the problem. So if we let AB meet CO at P here, since triangle AOP is congruent to triangle BOP by SAS, we have angle APO equals angle BPO. These angles together make up a straight angle. So if angle APO equals angle BPO equals 90 degrees, and then triangle APO and triangle BPO are just 30, 60, 90 triangles, right? Therefore, again, if you know one side of that triangle, you should find the other two sides. So in that case, AP equals half of AB equals 90. Then we have AO equals AP times 2 over square root 3. This gives us 60 square root 3, right? And we have AC plus CB equals AO plus BO. This gives us 120 square root 3. Then length, because of the central angle AOB is 120 degrees, so the length of AB, the length of arc AB is just 120 degrees over 360 degrees times the entire circumference, which is 2 times AO times pi, right? So this gives us 40 pi times square root 3. Therefore, the difference between arc AB with AC plus CB equals 40 pi square root 3 minus 120 square root 3. You get it? Okay, if you don't have any question, let's consider another question here. Triangle XYZ is equilateral with side length 10. A circle is constructed with center X and radius 10, thus passing through Y and Z. Can you find the area of sector YZX of the circle? So let's draw a diagram for you to illustrate the question here. Suppose this is a point Y, this is a point Z, this is the center point X. Okay, let's have a look at the solution together. So our sector is shaded in the diagram here. So to find this area, you must determine what portion of the sector is of the whole circle, right? Since triangle XYZ is equilateral, we know that this angle here is 60 degrees, right? Since the whole circle is 360 degrees, this means that our sector is just 60 over 360 times the area of that circle. In that case, the area of that circle is pi r squared, and we know r here equals 10, right? So this gives us the area of that sector equals 1/6 times pi times 100, which is 50 pi over 3. You get it? You have any questions? So put this in a summary. This tells us that we can find the area of a sector of a circle of radius r given the central angle of that sector. In the figure to the right, angle AOB is the measurement of angle AOB in degrees over 360 degrees of the whole circle, right? Therefore, we have the area of the sector AOB is the ratio between the angle AOB in degree measurement over 360 degrees times pi r squared. Again, actually you shouldn't have to memorize this formula, right? This is pretty intuitive. Instead, understand that the area of a sector is simply related to the ratio of the sector's angle to the number of degrees in a whole circle, right? Any questions? Alright, if no questions, let's do a practice here. So farmer Tim has 50 feet of fence. He wants to enclose a semicircular area adjacent to his barn. Using his barn as one side of the enclosure, what is the area of the space farmer Tim can enclose? And once you finish, please give me your answer in the chat box, alright? So, well, you could draw a diagram to illustrate the situation. Suppose this is one side of his barn, and this is an enclosure, right? Which is a semicircular area. And total length of the fence is 50 feet. Okay, I'll give you 1 minute to solve this problem. And once you finish, please give me your answer in the chat box, okay? Alright, have you finished? So if you want to find the area, usually you need to find the radius of the semicircular area, right? So we could start from the sketch of the problem here. Our fence from a semicircular arc, so the arc has length 50. So let's suppose the radius of that circle is r. Basically, we have half of the circumference, which is 2 pi r, is 50. This gives us the length of r, right? Well, this gives us r equals 50 over pi. Then the area of the semicircular area is 1/2 of pi r squared, right? And that is 1/2 times pi times r squared, which is 2500 over pi squared, and eventually the area is 125 over pi. The unit should be square feet. Any questions? Alright, great. So next, let's have a look at some more complex problems. But the method should be actually similar to what we have learned so far. So let's consider this question here. O is the center of the shown circle, and OA equals 8. The shaded region between chord AB and the circle is called a circular segment. Could you find the area of the circular segment here? Well, actually, circular segment or segment is the difference between two areas, right? It's the difference between the sector AOB and triangle AOB, right? And again, once you finish, please give me an answer in the chat box.
Sorry, I think I put it like it's 16. Yeah, sorry.
Number, right? All right.
Yeah.
Let's have a look at the solution together. So basically, you're finding the difference between the sector AOB and triangle AOB. So the area of sector AOB is, we have 90 degrees over 360 degrees times pi r squared, right? So pi times r is 8 here. So this gives us 16 pi, right? And we have the area of triangle AOB equals 1/2 of bottom times the altitude, which is 32. Therefore, the area of segment AB equals 16 pi minus 32, right? You get it? All right, any questions? Okay, if not, well, sometimes our region isn't ready drawn for us, so we must draw the region by ourselves in order to solve that problem. For example, let's have a look at this example here. If I have a barn that is a regular hexagon as shown here on the right, each side of the barn is 100 feet long. I tethered my burrow to point A with 150-foot rope. Can you find the area of the region in which my burrow can graze? So in that case, the region isn't ready drawn for you, right? You have to draw the region by yourself. You have to figure out what the region looks like. All right, let's have a look at the solution together. Again, as I said, first we need to figure out what region looks like first, right? Say the burrow is tethered at A, and roam so far that the rope pulls taut. Suppose the burrow keeps the rope taut and walks until part of the rope coincides with AB. The burrow then is at point G here, right? On the ray AB. Since AB is just 100 and the rope is 150 long, 50 feet long, right? 150 feet long, so BG equals 50 here. When the burrow moves beyond G towards C, then that's only 50 feet of rope for the burrow to use. And once the burrow moves past the G, the region he can reach is just the sector JBG, this small sector here, right? We have the same situation on the other side, so they are symmetrical in both sides, leading to sector HFI. Thus, our desired area is actually the area of major sector HAG plus the area of sector JBG plus the area of sector HFI. Actually, these two sectors are the same, so you only need to calculate once, right? Since angle ABC is 120 degrees, because ABCDF is just a regular hexagon, we have angle JBG equals, here, this angle is 6 degrees, right? Here. Therefore, sector JBJ, so we have area of sector JBG is 60 over 360 times pi r squared, right? Which is pi times 50 squared. And this gives us 1 to 50 over pi over 3. And the unit is square feet. On the other hand of the Gauss range is sector HFI, so that's basically the same, right? And finally, we have the sector between major arc GH and ready AG and AH. Since angle FAB is 120 degrees, then the other angle here must be 360 minus 120, right? Which is 240 degrees here. So the area of major sector HAG is 240 over 360 times pi r squared. In that case, r is 100 squared, which is you have oh sorry, this should be 150 squared, not 100. So eventually you have 15000 pi square feet here, right? And therefore the total area is 15,000 pi plus twice of this number here, right? This gives us 47500 pi over 3 square feet. Did you get it? So the key of this problem is to draw the area by yourself. If you identify the area you're looking for, things become much easier, right? All right, if you don't have any questions, you can also have a look at this question after this class. Let's have a look at another practice. So the shaded portion of the figure is called the loon. Given that AB equals 1, CD equals square root 2, and that segment AB and CD are diameters of the respective semicircles shown. Find the area of the loon. Okay, if you have any ideas, please give me an answer in the chat box, okay? Alright, let's have a look at the solution together. So we could start by noting that if we can find the area of this circular segment, then we could find the area of the loon, right? Because the area of the loon equals the area of the small semicircle subtracted by the area of the circular segment AB. Right? To get the area of the circular segment, we start by connecting its endpoints to the center O. Since the area of the circular segment AB, I'll just call it segment AB, okay? Equals the area of the sector AOB subtracted by the area of the triangle AOB, right? So we have the loon just equals the, well, if we put these two equations together, we have the area of the loon just equals the area of the small semicircle subtracted by the area of the sector AOB plus the area of triangle AOB. Okay, to find the area of sector AOB, we need angle AOB here, right? Since CD equals 2, we have OC equals OD equals OB equals OA equals square root 2 over 2. Seeing those square root 2's makes us think of 45, 45, 90 degrees triangles. So we check and see if that indeed the true. So we have AO squared plus BO squared equals 1/2 plus 1/2, which equals 1, which equals AB squared, right? So according to Pythagoras theorem, we know that angle AOB must equal 90 degrees, right? Then we can find the area of all our pieces. The radius of the small semicircle is 1/2. Therefore, we know the area of the small semicircle is just 1/2 of its area, which is 1/2 of pi r squared, which is oh, sorry, made a mistake here. This radius of that circle, the radius of that circle is 1/2, right? So that gives us ace pi. Okay, this one is solved. Then the area of sector AOB is 90 over 360 times pi r squared. And r is square root 2 over 2. And this gives us ace pi as well, right? Finally, the area of triangle AOB is half of AO times BO, which is 1 over 4. Therefore, we know the area of the loon equals ace pi minus ace pi plus 1/4, and eventually final result is 1/4. Did you get it? Okay, there is another question. Because of the time constraints, we could not finish. Please have a look at the solution. Have a look at the question here. Take a snapshot of that. We'll have a look at the solution in our next lesson. Okay, so there are a bunch of questions you should have a look at after this class. So in our next lesson, probably we won't have any new lessons, but have a look at all the homework questions there. Okay, so please do complete these questions after this class and submit your solutions in the Google Classroom at least one day before the deadline. All right, and please submit in one single PDF so I can mark them. All right. And okay, if you don't have any questions, class dismissed. I'll see you next time.
Thank you. Bye.